Hello. In this lecture, we will go and target the analog inputs, and we will see that we do not have in the Arduino Uno an analog output, but we will see how can we do this in another manner. So in the last lecture, we tackled the digital input output, and we saw that we have 14 digital input output that we can use as inputs as well as outputs depending on how we specify this pin to be. So this digital pin can be an input or an output. However, as for the analog, we only have analog input in the Arduino Uno. So here, in the case of input port, we do not need to have the pin mode, which is to specify if it is an input or output, because all the analog are input generally, and they are between from A0 to A5 in Arduino Uno. So we have 6 pins that behave as analog input. So in fact, what we have is we have an analog to digital converter inside the microcontroller, and inside the Arduino we have a 10-bit analog to digital converter. So K equal to 10 with V max equal to 5 volt and V min equal to 0 volt. So we can directly know what is the resolution of any analog input. It's equal to V high minus V low over 2 to the power K minus 1. So V high is equal to 5 volt, V low is equal to 0, and K is equal to 10. So the most important function here is called analog read. So I will be reading from the analog input the value. So when we call this function, we put, replacing here the pin, A0 to A5, depending on how I am connecting my signal to the microcontroller. So what will be the output of this analog read? The output of the analog read function is a value between 0 and 1023. Since we have 10 bits, so it's between 0 and 2 to the power 10 minus 1. So this is 2 to the power 10 to 1024 minus 1, 1023. So 0, output of 0 will be corresponding to 0 volt, and the function output of 1023 will be equal to the voltage, or will be corresponding to the voltage input of high. Generally it's 5 volt. We'll see we can change this value. So this is how we set. So sensor value equal analog read A0. It's very important to always remember that when we put it like this, we are reading from an analog input A0, and the value here, the output, is a value between 0 and 1023. Okay, so this is what I can say in fact about the analog read pin. So we have also to understand, oh, it's removed here, that the resolution in this case is equal to 4.8. So it was a 5 volt minus 0 over 1023 being 2K minus 1. So it is equal to 4.8 millivolts. So any value, analog value, below 4.8 millivolt as input cannot be seen at the output. So this is the resolution. So it's 4.8 millivolts. So for us, maybe it's small, depending on the application. We should see that in some application this is tremendously high. So this is why it's important to amplify my signal before going into the A to D or the Arduino. Okay, so basically in the Arduino Uno we do not have an analog output, so we will not be able to output a value of voltage, any voltage we want from 0 to 5 volt. However, and we have seen this when I discussed a little bit about the digital to analog converter, is that, okay, if I do not want to have a value exactly in terms of analog, what we can do is we can output a digital signal, but the device will understand this digital signal as an analog. And the only way to do it is through a pulse width modulated signal. So the pulse width modulated signal is a signal going from 0 to that can have only two values, 0 volt and 5 volt, but it is based on the frequency and the high time of the signal. So if I want to specify this as a PWM, so as you can see, this PWM signal can only take two values, which are 0 volt and high 5 volt. However, what is important is what is this high time here with respect to my period of the signal, and the ratio of high time over period is called the duty cycle. So this duty cycle can change from maybe, for example, here 10% to 90%, which is something like this. So the good thing is that I can do this PWM following what we have done in the previous lecture. I will put a certain give a certain high output to the pin, do a certain delay, then give low digital write, and then delay digital write high, delay digital write low, delay. The problem in this case is that first, the advantage is that I can specify the duty cycle I want, I can specify the frequency I want. However, the limitation or the drawback of such a method, which I call a low-tech PWM method, so is that I am just keeping the CPU busy just outputting a PWM, which is not very practical. Consider I have a flying drone that I need that it is quadrotor, so it has four rotors, four motors. So I need to output four different PWM, and in the same time read from the accelerometer, inertial navigation system, the gyroscope, the altitude sensor, and then do the autopilot with the closed loop control. So it's really unpractical just to keep the CPU busy just outputting a PWM. The good thing in the Arduino is that in most of the microcontrollers, in fact, they have what we call a PWM engine. So what we will do is we will specify one time which PWM I want, on what pin what is the duty cycle of it, and the PWM will start. And using this, I will use the analog write function. It has two input variables. I should specify what is the pin on which my PWM should output and what is my duty cycle that I want. So in using this function, in the Arduino Uno, we have just 6 outputs that in fact, these are digital input-output, but these output can be used as PWM. 3, 5, 6, 9, 10, and 11. And they are marked with a tilde sign beside the number. So this is in terms of the pin. As for the duty cycle, I cannot specify, we know that the duty cycle in reality is between 0% and 100%. But here I should specify on an 8-bit. So this duty cycle that I should feed my function with is a value between 0 and 255, corresponding to an 8-bit. Okay, so when I send a 0, it corresponds to a 0% duty cycle, so it's 0 volt. And when I send 255, it corresponds to the value of 100% duty cycle. Any value in between these two endpoints provide a corresponding duty cycle. So I can have a linear relation between 0 and 255. So for example, if I want a 50% duty cycle, I will send around 122. Okay, so in this case, I mean here 128, sorry. So in this case, the duty cycle cannot be a decimal value. It is an integer value between 0 and 255. Let's take this example. Consider an LED connected to pin 5. So pin 5 is one of the pins that can be used as PWM. What is the purpose of this code? For creating an integer I equal to 0, I plus equal 5, so here it's my new I is equal to my old I plus 5. So it's an increase by 5 for after each loop. And whenever I is less than 255, analog write on pin 5, I, and then delay 20. So let's first, before going into the application, let's explain the instructions as is. So here I am writing an analog, so an output. My output here is a PWM on pin 5, and this PWM duty cycle is increased from 0 by steps of 5 till 255 with a certain delay of 20 milliseconds after each one of these increase. So here, if this is connected to an LED, what you see is you start with the LED off, and then you see the LED light going brighter, 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 brighter till it arrives to a full 100% duty cycle. So and when you go into and increase this delay, this increase of the brightness of the light will be slower. So a very simple application where this analog write is used connected to an LED. So we talked about the duty cycle here, as you can see in the analog write, but we do not talk about the frequency. So unfortunately, or maybe for some fortunately, the frequencies are fixed in an Arduino. We will see later when we go into timers that these can be changed, but we have to go really deeply into the Atmel microcontroller. But here, talking with the high-level Arduino without going deep into the Atmel, these frequency cannot be changed. And most of the pins, they have a frequency of around 490 Hertz. Only pins 5 and 6, they have a frequency of 980 Hertz, okay, which is double the frequency on the other pins. These frequencies work quite well with small DC brushed motors. They work quite well with LEDs, with tone output, tone frequency. So they are really good for everyday use in mechatronics system if you want. But if you need to control more these frequency, yes, you can do it. And we will tackle this in the advanced Arduino part at the end of the semester. So here, if I want really to go into these, we have to pay attention on something. the analog read function that we covered take the analog input voltage as input, and it outputs a number between 0 and 1023, since the A to D converter inside the Arduino is a 10-bit. The analog write function only works with values if I want to specify a duty cycle for it between 0 and 255, which correspond to 8-bit PWM. So if I want, for example, to read the function, or let's take an example. I want to connect my thermistor to the Arduino. The thermistor will be detecting the temperature, and based on this temperature I want to feed a duty cycle in order for a fan to go on. Typical example is your PC fan. You have a thermistor inside your laptop, for example. It measures the temperature of the CPU, and you have steps. So for each temperature, this temperature will go and give a duty cycle. When the temperature is very high, you see that the fan will be turning in a very fast way. When the temperature is low, the fan will not be turning, or it will be turning in a very slow movement. So if I want to go this analog read and put it directly in my duty cycle, this cannot be done. It will give me error, and it will give me that duty cycle value will go above 255, which will not be understood by the analog write. One way, and one very easy way, is to say, great, I can divide by 4. So from 0 to 1023 divided by 4, any value will give me a value between 0 to 55. Great, and this is something that can be done. However, if I am sure maybe that my voltage cannot go above 800, dividing by 4, I am losing a very large part of accuracy. Okay, so what can I do in this way? So here I want to go into the resolution. Getting into the resolution of the A/T converter, so it is equal to V high minus V low over 2 to the power k minus 1. So if I want to improve this resolution, so improving this resolution means to minimize it. Minimize it, I have 3 options to minimize this resolution. The first option is to decrease VH. This case can be applied if I know that, for example, my sensor voltage goes from 0 volt to 3.1 volt only. Okay, why I should put V high equal to 5 volt and lose everything between 3.1 and 5 volt? I will be losing all of this range. What I can do is I can put V high equal 3.1, and now my 3.1 volt will be corresponding to 1111111 as output of the A to D. The second option is to increase VL. Okay, so maybe my sensor cannot go up low to 0 volt. It's the same idea. The third option is to improve my A to D converter with increasing K. Not using, for example, a 10-bit, using a 12-bit, not using a 12-bit, using a 16-bit. What of these 3 options can be applied in real life on the Arduino? First, this cannot be applied since the Arduino is made with a 10-bit A to D converter integrated in it. So I cannot change K. Generally, practically, most of the sensors, they have ground as reference and then go up. So this is not a very good practical system or way in order to optimize my resolution. The only way that is remaining is to decrease the high voltage, not 5 volt, depending on what I have, and this is done on the Arduino by using the analog reference. So the analog references is a function where you can input one of the three cases. Okay, the first case is you can put analog reference internal, and in this way you are setting the voltage high to be 1.1 volts. You can put by default, and if you don't call this is default, but you can call default just to be on the safe side. Maybe it takes the +5 as a voltage high. But maybe I need 3.8, 3.9. You can have this option by setting analog reference external here, put the type as external, and put the value of voltage that you want on what we call the AREF pin. So if you go onto your Arduino board, there is beside the analog inputs, there are the AREF pin. This AREF is a pin where you connect a voltage to it, and this voltage between 0 and 5 volt, of course, and this voltage will be my high. It could be 4.1, 2.8, 3.2, depending on what you have as application. This function is only called once in a sketch, but must be declared before you are reading, of course, in order for the analog to digital converter to know what is its resolution. It's not necessary to put this. If you do not put any analog reference, it will be taken as default to be 5. If you want to change it, to change this high, you will put analog reference. Is a very nice candidate to be put in the void setup, because I just want to run it once in order to tell the A to D converter what is my high voltage, and then I can continue with my loop. Remember to never connect the AREF pin to a voltage source, of course, greater than +5, because this can damage the microcontroller. So AREF can take any value between 0 and 5 volts. So there is a nice way to see the values, because when you are connecting the Arduino, you upload your code to the Arduino, but you cannot see exactly what values in order to optimize your code, in order to change your code, in order to debug your code to see what are the errors inside your code. A nice way is what we call the serial monitor. The serial monitor can be accessed on this by clicking on this icon on the Arduino software. But you have to specify some code before in your sketch in order to be able to see the serial monitor. When I want to use the serial monitor, you know that when I am now we have discussed, when I am doing the analog read function, the output of the analog read will be a value between 0 and 1023. If I want to see what is this value, okay, this is a nice way to calibrate, for example. Okay, so this is a temperature. I am having a temperature sensor connected to my voltage input, and it's giving me as output 900. What is 900? So what is 1000? What is 5? So I need to calibrate this with respect to the values that this analog read is giving me. The serial monitor is a nice way to do this. This is an example. So, for example, if I am connecting my analog, my sensor to my analog pin A0, in the void setup, I will put serial begin 9600. What's this? Since the serial monitor is a serial connection with the A2D, with the Arduino, I need to specify what is the speed of the serial connection. I will not go into serial communication in details, but here what I am specifying is to begin the serial connection. So this is serial.begin, and here I am specifying 9600 bits per second. Okay, and this is the speed that you should set in your setup function in order to see the output on the serial monitor. So here I am reading from A0 analog read, and I am putting the value which is between 0 and 1023 in an analog value integer which was created before. And then I am printing analog value equal. So when I say serial print analog value, so everything between these codes will be put as is. Then serial print new line, this is ln, so it will print on the new line, and here you will put the analog value. Okay, DEC is one option. If this is a decimal, it can be set as decimal, but here in this case analog value is between an integer from 0 to 1023, so it will not be, I will not be using the decimal here. So here I will be putting analog value equal. Next line I will put the value, then delay 125 millisecond, then reading again from A0, printing again analog value equal, and printing again the value that was read from the analog read. So you will see analog value equal 200, analog value equal new line 100, etc., etc. So here you can see by changing the temperature maybe on the sensor, you will see what are the values that are output on this. Map. So here also, and this is a linear relation, here also if I want, for example, to have values, this is one of the questions, one of the answer of this question here. Okay, how can I improve the accuracy? So I can map. What do I mean mapping? So here, for example, if I have a value that is scaled between 0 and 1023, and I want to put this value between 0 and 256, I will use the map where I will put the value. This value is in the initial interval, and the output of this will be the same value in this interval. So the map is value, which is maybe a variable, then from low, from high will be the values, the low and high values that we are beginning with, expressed as constant or variable. So this is the start interval, and this is the destination interval, too low, too high. When can I use this case? Let me assume that my sensor gives me, after the A to D conversion, a values between 0 and 800. Okay, one of the solutions in order to improve the resolution, we said that let's decrease VH. Decreasing VH maybe to 3.75 will do the job. However, in the case of decreasing VH, I need to create a 3.75 voltage and connect it to the AREF pin. So it's not a very easy task if you want. But what I can do is I can do map, and saying that from 0 to 800, I will go from 0 to 256. So in this way, I will not be dividing only by 4. I will be losing here 800 to 1023, but this loss will not be reflected between 0 and 256, and thus in this way I'll be improving my resolution if I want to use it in another interval. So, and this is not only the map is not only used for a 2D converter, it is used for any value that should be mapped from a start interval to a destination interval. Constraint. Constraint is, I can say, a saturation. Look at this, what I will be doing here. So consider that I have a value here, sorry, let me take the previous case, and I am saying from 0 to 800, and I am going from 0 to 256. I am sure that it cannot go above 800. But for a reason or another, I don't know, maybe an error, maybe a noise, maybe something that is unpredictable, there was one reading that can output a 900 here. This map will, all the code will stop, and this map will give you an error. This function will give me an error telling me that the value here is 900, is outside the start interval, so it cannot go to the destination interval, and it will give me an error. So in order to get rid of this, I can use the constraint. The constraint will tell me, great, I want a value that go from a minimum, let's say 0, to a maximum 800. Or if I want to really emphasize a general rule, so let's say this, I want it from 100 to 800. And by the way, this from low can be 100, not only necessarily 0, and this also. So let's take, I have a value that can go from 100 to 800. This is the sensor output of the A to D converter, can go from here to here. So what I will do is I will take a linear between, so when it is 100, my output is 100, and when it is 800, my output is 800. When my output is larger than 800, this is constrained to 800. And when my input or my output of the A to D converter is less than 100, the output of the function constraint will be always equal to 100. So constraint is used a lot before map in order to decrease the number of errors and bugs inside the map. So in this case, I will say constrain the value between 100 and 800. So if the value is between 100 and 800, my output will be this value. If this value is 900, my output will be the maximum, which is 800. And if the value is 50, the output will be the minimum, which is 100. So take this example. So here I am reading my analog value maybe from an analog read function. So it comes from a sensor maybe, and it is 0 to 1023. But I am sure that what is interesting for me is all these values of the sensor corresponding to output between 10 and 900. So in this way, I will constrain my analog value to 10-900 interval. Anything in between will be the same. Less than 10 will be equal to 10. Larger than 900, it will be equal to 900. And I will put the value in analog value in the same. I can put here another variable, but it can be the same variable. Then now I will map the value after the constraint, and I will tell the map function, I want to map this value from the start interval 10-900 to the destination interval 0 to 55. Okay, and in this way I will be mapping, and here I will be minimizing the errors or even removing all errors because here I am sure that this value can never go beyond 900 or below 10. Why? Because I constrained it here to have a value between 10 and 900. So in this way, I will say that I finished this part of analog input and PWM output.